Hi everyone. In this video, I want to talk about section 2.5, continuity. Intuitively speaking, a function is continuous if the graph of that function has no holes or gaps. So another way of saying that is if I were to trace the graph of that function, if I could do so without lifting the pencil at any given point whatsoever, then that function should be continuous. So for example, one function that is continuous might look something like, so let's say here's the x and y, and as long as I can trace a graph without lifting the pencil, so maybe it's gonna look something like this. So this is definitely continuous. Now let's give some examples of functions that are not continuous also. And it's really not that hard to do, right? Because I just need to create some gaps or holes in them. So maybe the one with the holes might look something like so. And the ones that have gaps, I guess, now the gap can be finite or infinite, so it could be something like this would be where you have that finite gap, but also it could happen that you have something like a vertical asymptote where you have infinite gap like this. So at this point, maybe you have this vertical asymptote at that value, something like this, right? So you definitely do have this infinite gap at this x value right there. So these three would be some examples of functions that are not continuous. Now, of course, as a calculus student, you want to be able to go beyond this intuition. So we want to talk about this precise definition of what it means for a function to be continuous. So let's take a look at what the textbook says as the definition of continuity. If you look at page 118 of your book, at the beginning of section 2.5, you see this definition in the box, definition 1. A function f is continuous at a number a if limit as x goes to a of f of x equals f of a. Now, one thing that I want to point out is what it says after that. It says, notice that definition 1 implicitly requires three things if f is continuous at a. So what I would like you to do is to actually understand exactly what the definition implies as three conditions that each function has to satisfy in order for that to be continuous at particular value of x. I want to go back to those graphs that we drew as examples of functions that are not continuous and analyze which one of these three conditions fail to be true. So before we go back to that, I would like you to have these three conditions available in front of you. So let's number these examples of functions that are not continuous. So let's just call this one 1. This one is 2. This one's, let's say, example number 3. So going back to those three conditions, if you look at graph number 1 and graph number 3, notice that both of these functions at this x equals a, so let's just call that value a. At x equals a, the function value is not defined. So f of a is not defined. So notice that right off the bat, number 1 and number 3, you can conclude that this is definitely discontinuous. Now number 2, this one is a little bit different, isn't it? Because say that this is x equals a. Do notice that the condition number 1, f of a is defined, definitely defined because there is a point corresponding to that x value. But what this function does not satisfy is condition number 2, because the limiting value of this function, notice that going from the left, function value goes towards that hole there, but from the right it goes to that dot that I just drew. So limiting value going from the left and going from the right, there's no unique value that the function is approaching, so the limit doesn't exist. So number 2 definitely fails to hold that condition number 2 to be true. So how about a function, example function where the limit exists at x equals a, and also the function value is also defined, but is it possible that the function is going to be discontinuous because condition number 3 fails to be true? So I want you to think about that a little bit and see if you can come up with that example. So pause this video if you need to, and I want you to think about that before you move on. Okay, so let's call this example number 4. Now what we want to do is to come up with an example of a function that is not continuous at x equals a, but f of a is defined and the limit actually exists as x goes to a, but it fails to be continuous there because condition number 3 fails to be true. So I don't know if you could come up with that example or not, but here's one. So suppose that this is where x equals a. So this function that I want to draw is going to be discontinuous there. Now the limit has to exist, so that means that as the value of x goes to a, function needs to try to approach exactly the same value. So it would have to look something like this. But now if I just create the hole there, then the function is not defined at x equals a. Now if you look at that condition number 3, limit has to equal to the function value. So in order for it to be discontinuous, then let's say that the function value is defined somewhere else other than that hole. So the limit exists because they both approach that y value, and function is definitely defined because there's the dot there. But in this case, the limit as x goes to a does not equal to f of a. So as you can see, this is definitely not continuous. So this graph number 4 is also an example of a function that is not continuous. Now I already used this terminology earlier, but if you happen to have a function that is not continuous at x equals a, then we say that there is a discontinuity at x equals a. So in order for us to say something is not continuous, another way of saying that is example number 1 through 4, these are functions that are discontinuous at x equals a. So before you come to class to talk about 2.5, I would like you to know the actual precise definition of continuity of a function at x equals a, and be able to identify when something is discontinuous, which one of these 3 conditions fails to be true. Now I want to focus on that third condition, which it says that the limit as x goes to a of f of x must equal to f of a, which if you look at that definition, that third condition is the actual definition of continuity at x equals a, right? So I want to think about what that is telling us as far as what we can do to evaluate limits of functions that are continuous. So let me just write down the third condition of continuity, or another way of saying that is this is actually the definition of continuity, right? So limit as x goes to a of f of x has to equal to f of a. Now, if you stare at this statement for a little bit, you realize that if you happen to know that function is continuous at x equals a, the only thing that you have to do to evaluate the limit is to literally just take that value a and plug it into that function expression. So I want you to actually realize how powerful this is. So again, let me say this again. If you know that a function is continuous at x equals a, in order for you to evaluate the limit as x goes to a of that function is for you to take that value a and plug it into the function itself to evaluate the function, because the limit is going to be exactly the same thing as the function value. So that means that if you know that certain functions are continuous, then you don't have to use any of the tables of values. You don't need to even look at the graphs, or you don't have to even rely on those limit laws that we studied and used in section 2.3. So at this point, let's just think about functions that are continuous, that we know to be continuous. So essentially, those functions that we identify, all you need to do is, as long as those are continuous, then we can just take the value and plug it in to evaluate the limit, right? So I want to take you to this page in the textbook. This is page 123, and in the book, it's listed as theorem number 7. But take a look at this. It says that the following types of functions are continuous at every number in their domains. Now, if you look at the list given here, you probably remember the set of problems in the algebra review that I gave you. I had a list of functions where I asked you to identify the type and the domain, right? I also asked you to identify the range, but that's not really relevant for this theorem. But those functions, or these functions that you see here, if you can identify the type and also the domain, in order for you to evaluate the limit of any of these functions, as long as the value that you want to approach happen to be in the domain of these functions, then all you need to do is just plug the value into the function. So it's going to give us a lot more useful tools for us to evaluate the limit. So at this point, what I want to do is to give you a couple of simple examples to show you how to use this theorem. Okay, so for both of these examples, notice that in example number 1, that's a polynomial function, and -1, x is going to -1, and since -1 is in the domain and polynomial is continuous everywhere, so to evaluate this limit, all I need to do is just plug that -1 into that function. And the second example, that function is a rational function. Rational function is, the domain of that is all values of x except for the ones that would make the denominator 0. Now, if x is approaching 2, that is definitely in the domain, and rational function will be continuous at x equals 2. So to evaluate this limit, I don't have to apply any limit laws or anything like that. All I need to do is to plug that value 2 into x. So this is what we get. So no tables to create, no limit laws to apply, just simply plug the value in.